Welcome to this deep dive into a remarkable engineering feat from Pinterest. Today, we're unraveling the sophisticated strategies Pinterest employed to tackle a ubiquitous challenge in large-scale software development: sluggish Git clone operations. For many organizations, especially those managing vast monorepos with extensive commit histories and numerous contributors, the time taken to clone a repository can significantly impede developer productivity and CI/CD pipeline efficiency. Pinterest, known for its visual discovery engine, faced this very predicament. Their engineering team embarked on an ambitious journey to drastically reduce these clone times, ultimately achieving an astonishing 99% speedup. This presentation will explore the why behind this necessity, the how of their innovative solutions, and the profound impact on their engineering workflow, offering valuable insights for anyone dealing with similar scalability issues. At Pinterest, the codebase is not merely large, it's a colossal monorepo, housing virtually all of their application logic and services. This architectural choice, while offering benefits in dependency management and consistency, presents significant challenges when it comes to source control operations. With thousands of engineers contributing daily and hundreds of thousands of automated CI/CD jobs running constantly, a slow Git clone operation multiplies its inefficiency across the entire organization. Even a few minutes added to each clone translates into countless wasted hours of developer time and substantial delays in their continuous integration and deployment pipelines. This directly impacts the pace of innovation, the speed at which new features reach users, and ultimately the company's ability to compete effectively in a fast-moving digital landscape. Optimizing this fundamental operation was not just a convenience, it was a critical business imperative to maintain agility and accelerate development cycles. To effectively optimize Git clone times, it's essential to understand what happens under the hood. When you execute Git clone, Git performs several key operations. Initially, it retrieves references and then fetches all objects, commits, trees, and blobs required to reconstruct the repository's history and working directory. A crucial aspect here is Git's use of pack files, which store objects in a compressed, delta-encoded format to save space. While highly efficient for storage, transferring these large pack files over a network can be time-consuming. Furthermore, the client-side process of decompressing and reconstituting these objects, especially with deep histories and numerous unique files, can be CPU-intensive. The larger the repository history and the more distinct objects it contains, the more data needs to be transferred and processed, leading to the slowdowns experienced by Pinterest engineers. This detailed understanding allowed Pinterest to pinpoint specific areas for intervention. Before landing on their groundbreaking solution, Pinterest, like many large enterprises, explored common Git optimization strategies. Early attempts included implementing shallow clones, which limit the history depth, and partial clones, using existing Git features that allow excluding certain blobs. They also invested in robust network infrastructure to minimize latency and maximize bandwidth. While these tactics offered some incremental improvements and are effective for certain use cases, they ultimately proved insufficient for Pinterest-specific challenges. The sheer size and complexity of their monorepo meant that even with shallow histories or basic partial clones, the amount of data still being transferred remained substantial. Furthermore, the need for developers to access specific parts of the repository, sometimes with full history for those sections, highlighted the limitations of these one-size-fits-all approaches. Pinterest recognized that a more granular, intelligent, and tailored solution was required to achieve significant impact. Delving deeper into the root cause, Pinterest identified that the core problem wasn't just the volume of data in the monorepo, but how that data interacted with network bandwidth and latency. Even with Git's highly efficient delta compression, the sheer magnitude of objects to be transferred, especially during a full clone, stressed network resources. Imagine downloading gigabytes of data multiple times a day across thousands of machines. This creates an enormous burden. Network latency, though often overlooked, further exacerbates the issue. Each round trip for object negotiation and transfer adds precious milliseconds that accumulate into significant delays over a large number of requests. For a globally distributed team and numerous geographically dispersed CI/CD servers, these network characteristics became a critical bottleneck. This made it clear that reducing the amount of data being transferred was paramount rather than just optimizing the transfer speed of all data. The breakthrough for Pinterest came with a deeper exploration and innovative application of Git's partial clone capabilities, specifically leveraging a feature often referred to as object filters. This approach moved beyond simply excluding certain file types and focused on filtering the Git object graph itself. Pinterest developed a sophisticated internal toolset and methodology which we can conceptualize as their Promisor system. The core idea behind Promisor was to enable clients, whether a developer's workstation or a CI/CD build agent, to request only the specific Git objects absolutely necessary for their current task. Instead of downloading the entire repository's history and all its files, they could specify exactly which parts of the codebase or even which historical revisions they needed. This highly targeted approach promised a dramatic reduction in data transfer, directly addressing the bandwidth and latency issues that plagued their Monorepo workflow. The elegance of Promisor lies in its intelligent object filtering mechanism. When a developer or a CI job initiates a clone, instead of a blanket request for all repository data, the client sends a highly specific request to the Git server. This request might specify a particular subdirectory, a limited history depth for that subdirectory, or even a set of file paths relevant to a single microservice within the Monorepo. The Promisor system, residing on the Git server infrastructure, intercepts this request. It then dynamically analyzes the Git object graph and constructs a custom pack file containing only the objects that match the client's filters. This means that instead of transferring gigabytes of irrelevant data, the client receives perhaps only megabytes. The server performs the heavy lifting of identifying and packaging only the essential objects, drastically minimizing network traffic and subsequent client-side processing, thereby addressing both bandwidth and CPU concerns simultaneously. Implementing the Promisor system was not merely a software development task. It required significant changes to Pinterest's existing Git infrastructure. This involved extending their custom Git server implementations, likely based on or integrated with services like GitLab or custom Git daemon setups, to support the new object filtering capabilities. Crucially, the client-side Git tooling also needed to be updated to intelligently construct and send these filtered requests. This integration meant modifying existing developer workflows and CI/CD pipelines to automatically leverage partial clones where appropriate. Pinterest ensured a seamless rollout by carefully integrating Promisor into their internal CLI tools and build systems, making the optimization largely transparent to engineers. The team faced challenges in ensuring compatibility, maintaining performance under heavy load, and educating their vast developer base on the new best practices. But the benefits far outweighed the initial investment in infrastructure and integration efforts. The results of Pinterest's Promisor initiative were nothing short of transformative. By intelligently filtering Git objects at the server level, they achieved an incredible 99% reduction in clone times for many common developer workflows and CI/CD jobs. What once took several minutes or even longer for a full Monorepo clone could now be completed in mere seconds. This dramatic acceleration had a ripple effect across the entire engineering organization. Developers experienced significantly less friction and wait time, leading to higher morale and increased daily output. CI/CD pipelines, which previously bottlenecked on Git operations, now executed much faster, enabling quicker feedback loops and more frequent deployments. This wasn't just about saving time, it was about empowering engineers to iterate faster, experiment more freely, and deliver features to Pinterest's users with unprecedented speed and efficiency. The 99% speedup directly contributed to a more agile and productive development environment. Pinterest's success with Promiser offers invaluable lessons for any organization grappling with large-scale Git repositories and slow clone times. Firstly, it underscores the power of deeply understanding the underlying mechanics of your tools, in this case, Git. Rather than applying superficial fixes, Pinterest delved into Git object model to find a truly impactful solution. Secondly, it highlights the importance of custom tooling and infrastructure tailored to specific organizational needs, especially at immense scale. Generic solutions often fall short when confronting unique architectural or operational challenges. The techniques employed by Pinterest, particularly the intelligent application of Git's partial clone features, demonstrate a path forward for other large engineering teams. As codebases continue to grow, the demand for such smart, targeted optimization will only increase. This commitment to optimizing fundamental developer experiences is a hallmark of truly innovative engineering, proving that even seemingly minor operational improvements can yield monumental returns in productivity and business agility.